framework of my PhD. So let's start to introduce our context. We work in what is called direct-to-cell communication, which is basically a direct link between the satellite and the user equipments. And so for this application, we will rely on future trains. And as we will have many simultaneous users, we will also need many steerable beams. One of the promising technology for this is large active phase array. And then we are interested in obtaining the beamforming, but also the nonlinear distortion, the IMD interferences from this system. And also, as we have a large number of power amplifiers, we are interested in the efficiency of the full system. Nevertheless, such a technology will raise some challenges. As you can see in the literature, most of the antenna pattern and radiation pattern analysis are done without the PA nonlinearities. The reason is because when we increase the number of power amplifiers, we can start to have some issues in terms of convergence and also in terms of computation time. And yes, most of the commercial software are actually not suitable for these simulations. That's why we had this interest in a digital twin of an active integrated antenna array. Basically, in classic design of active phase array, we use what is called isolators. They prevent the signals coupled from the neighbors that to come in the output of the power amplifier. So basically what we do is to fix the load to 50 ohm to match the power amplifier. The problem with isolators is that they are bulky, not easily integrated. They increase the mass and the cost, and they also introduce some power losses. That's why it looks like the industry is moving toward removing them to use what is called active integrated antennas, where basically the power amplifier is directly matched to the antenna. The problem with that approach is that the power amplifier load will vary with the beamforming due to the mutual coupling. It's commonly referred as load pull effect. And it's well known that the power amplifier performances are actually dependent on the load. And then, due to load pull effect, it starts to be complicated to anticipate the beamforming and the efficiency of our full system. As an example of load variation due to load pull effect, I will introduce a simple iterative loop approach, where basically when we have the input signal and the power amplifier characteristics, we're able to create a power amplifier model that will at first consider a matched power amplifier, then compute the output signal from it as a matched power amplifier. And with the mutual coupling from all the other neighbors, we'll be able to compute what we call active efficient coefficient, which is basically the load that is seen by the power amplifier. If this load is equal to 50 ohm, then we have our output signal or active efficient coefficient. But if it's not, it means that we can compute a new active efficient coefficient from the output signal we computed. And then we can compute a new active efficient coefficient, and we can reproduce this process again and again until we have convergence. At the end of this algorithm, we are able to compute the variation in time and due to the beamforming of the load seen by our power amplifier. Here is an example of 91 radiating elements hexagonal active array without isolators. And you can see that it's quite difficult to anticipate how this load will vary in time. That's why we work in power amplifier modeling, and I will present a few models. The first model I would like to present is called circuit envelope simulation, and it's commonly used in commercial software. Basically, when you have your complex envelope, you can sample it and have different time instants. At each time instant, you can then compute the output spectra. And depending on the time variation of this spectra, you can anticipate the behavior of your power amplifier, and you can compute the output complex envelope. That's basically what we did with this class AB power amplifier designed at Heriot Watt University, and that Jiayu will present later. And you can see here that we have different microstrip lines, and we also have the transistor model from the manufacturer. And due to that, and with the circuit envelope simulation approach, we're able to have a very interesting model because it takes into consideration memory effects, which means that the instantaneous power amplifier response also depends on the previous responses. And this model is very accurate, even for wideband application, and can account for dual input, so a complex envelope both at the input and output ports of the power amplifier. The limitation of such an approach, so I already told them, is the efficiency in terms of computation time. We can also have some issues of convergence. And that's why we worked in other power amplifier models. And one of them is the lookup table. Basically, it can be seen as an amplitude and phase bilateral memoryless model, but defined for a large range of loads. Basically, in your Smith chart, any load you will take will be associated to two curves of amplitude and phase modulation for a specific range of input power. Which means that if you know the input power and the load that are applied to your power amplifier, you can anticipate its behavior, its instantaneous behavior. This model is relatively fast once you measured or simulated the lookup table. It's especially mathematically simple and really easy to implement in an algorithm, and it can account for dual input. The main limitations are that it's memoryless because we don't take into consideration the past of the signal. And it's also limited to reflection coefficients out of the Smith chart. Otherwise, it doesn't make sense to take a load pole measurement. And we are, of course, limited by the resolution of the lookup table in terms of accuracy. Then I would like to introduce what is called the polyharmonic distortion approach. So again, if we take our complex envelope and we sample it in multiple time instants, and if we take this representation of a power amplifier with A waves being the incident wave and B wave being the output wave for both port 1 and port 2, if we consider that the power amplifier is well matched at the input and then B1 is equal to 0, we can say that B2, so the wave we're interested in, is equal to a nonlinear function of A1 and A2. Then, assuming that the input power is higher than the power from the mutual coupling that is explained by the power amplifier, we can use what is called a linearization, or in other words, a first-order Taylor series expansion. And so basically, if you take only the first order of your Taylor series expansion, you can write this specific formula where we explain that B2 is supposed to be function of A1, A2, and the complex conjugate of A2. We also have some coefficients, S21, S22, and T22. These are not S parameters, because as you can see, they depend on the input power. And then these coefficients can be extracted by measurements or by identification with power amplifier behavioral model, and I will tell a little bit more about that later. This approach is interesting because it has fast computation, as we have only 3 coefficients to measure. It's mathematically simple, and it can account for dual input. The main limitations are, again, we don't have memory, we don't take into consideration the past of the signal, and it's not really accurate for load variations. And that's why some people developed enhanced PhD or ePhD approach. So basically, we keep exactly the same approach, but instead of keeping only the first order of the Taylor series expansion, we will go until the third order. And then you can see here that B2 will be equal to the first PhD model I just presented, but will be also dependent on some extra coefficients to improve the accuracy. And then it enables us to take into account the nonlinear influence of the load impedance variations while keeping a straightforward model extraction methodology. The main advantages are that it's still fast in terms of computation time. It's more robust than PhD model to load variations. And again, it can account for dual inputs. The main limitations are, again, that it's memoryless and that it's not really suitable for very high mismatch. And then I would like to introduce the Chalmers approach. So in the public, we have some of the creators of this model. So I'll try to explain to do my best to explain my understanding of it. Of course, if something's wrong, do not hesitate to tell me. So the Chalmers model is basically a generalization of the ePhD model with an extension to memory. So instead of considering only the third order, we will consider until the nth order. And they managed to find a specific formula that will take into consideration all the parameters for all the orders. And then by doing identification with memory polynomial approach, they managed to replace the coefficients. So S21 is now dependent on the parameter of polynomial coefficient, and that's the same for the A2 and conjugate A2 parameters. And actually, you can see that the first line is a classic memory polynomial model. And this model is very interesting because it's fast. Once the coefficients have been calculated, it can account for dual inputs. It has memory, and it's accurate even for high mismatch that make it suitable for wideband modulated signal. So here is a summary of the few models are presented to you today, and you can basically see that Chalmers is the most interesting model for now in terms of accuracy of time computation, and also because it takes into consideration the memory effects. I also did some simulation to do comparison in terms of computation time and in terms of accuracy between the lookup table model, the Chalmers model, and the complex envelope simulation approach using the commercial software ADS. I generated new radio QPSK FDM signal, which is basically the signal applied to direct-to-cell applications. And we did a comparison for one power amplifier for full frame. So really a large number of points. Considering that A2, so the injected wave at the output port, is -5 dB lower than A1, which is actually higher mutual coupling than the studies array I have, we can see that, of course, ADS takes a really long time to compute everything. The lookup table is way faster with 45 seconds, and Chalmers takes only 4 seconds, taking into consideration the computation of the coefficients. Then in terms of accuracy, for this specific mutual coupling, we can see that ADS and Chalmers have very good accuracy, but the lookup table has a huge gap that can be explained for both the resolution of the lookup table, the limitation of the range of load we took into consideration, and also the memory effects that are not taken into consideration with the lookup table. But if we reduce the mutual coupling, now A2 is -10 dB lower than A1 for the same configuration, we can see that we can reduce this gap. And if we reduce it again until -15.8 dB, which is equivalent to the mutual coupling of the studied array I have, and I will present later, we can see that this difference in accuracy is not so strong. So the lookup table accuracy looks decent for this coupling level, even if the Chalmers model is still the best, both in terms of computation time and accuracy. All right, now I presented the power amplifier modeling approaches. I would like to speak about the antenna modeling we have. So basically, this is the 91 rating element array that Thales Alenia Space provided to me. And what is interesting to see is that if we take the edge elements, so from 1 to 6 in the side, you can see that the active element pattern from the element 1 and element 6 are actually different. It's due to the neighboring configuration. And you can see that if you go to the central elements, then we start to have an average and to have the same active element pattern for all of them, or almost the same. So then if we want to do extrapolation of our array, we need to take that into consideration. So this is our 91 rating elements array. And then if we want to extrapolate it to a 397 rating elements array, we'll have to allocate a specific configuration to each extrapolated element, like all of them will be assigned to a base 3 that has the same configuration. Again, the elements 397 here is actually allocated to the element 91 because they are very similar configuration. And we do the same if we increase the size of the array again and again. Then once we have this allocation of base, we can assign a specific active element pattern, and we can assign a specific S parameter matrix. Well, for the S parameters that are assigned to a larger distance than what we have with the 91 rating elements, we just put them at the minimum value we had. So basically, we neglect them. Then here are some results of an extrapolation of our 91 rating elements array with 397 elements with and without edge effects. So you can see that for some specific location, we can reach unto 0.5 difference when we don't take into consideration the edge effects. So it means that it still is interesting to keep into consideration them. And that's the approach we'll take for the next simulation. All right, now we have the power amplifier modeling and we have the antenna modeling. We can apply it to a direct-to-cell communication scenario. So basically, what we did is to compare our results with a 3GPP simulation baseline. And you can see that we have very similar results, even if our antenna array has more gain than what is proposed, which is an approximation of 3GPP standards. And we took the same parameters for the user equipment parameters. And then we developed a specific algorithm to generate some new radio or FDM signal for direct-to-cell communication, taking into consideration the allocated bandwidth proposed by standards and respecting the required OFDM, applying, in our case, QPSK with a bandwidth of 30 meg, which is like full bandwidth, and with a subcarrier spacing of 15 kilohertz, which represents 1,920 subcarriers per symbol. Once we have all these parameters and all this modeling, we are able to compute the C/n+i radiation on Earth. And that's what you can see right here. And then by taking a specific location on this pattern, we are able to compute the constellation that is actually received by the handheld user equipment. This constellation takes into consideration the non-linearities from the power amplifiers, but also the loss from the link budget analysis. And that's interesting because depending on these variables, so the antenna array size with possible extrapolation, the beamforming with the number of beams, beam steering, the backoff of the power amplifier, and then the modulation parameters, when we apply all these variables to a specific satellite configuration, like its altitude, for example, we are able to assess if our trade-off makes sense. Right. And besides, I would like to present just a few work we did in parallel. So basically, I think all of you know what is a CW-QPSK. And then when we go to OFDM QPSK, what we do is basically to change the sign to a sign card with a specific filtering. And we have different sign card function. And with a specific spacing, they don't have interferences between them, which means that it makes sense to try to model them to approximate them with multiple tones, as is presented in this paper. Based on that, we did some work using what we call the mixed frequency time approach with the Lucas-Bessel-Fourier approach. And it enables us to do extraction of IMD EIRP patterns and also to do comparison with the subcarrier EIRP patterns, and eventually to be able to do the computation of the carrier of the IMD3. And so based on that, we were able to do some statistical analysis of the IMD3 level compared to the subcarriers for different modulation, for different beam steering, so a full statistical study. And then we were able for different backoff to plot the PDF and CDF curves. Right, so that's all for me for now. I will let Jiayu present his her presentation. Yep.
So the background has already introduced by Aymeric, and here we're under exactly same topic, and we do realize that there are increasing number of research under this topic, but there is no relevant taskbar to support all the theory validation that motivate us to fabricate this active rate taskbar. So we'll start with the overview. Here is a picture of my active array taskbar, and frequency 3.5 GHz. We have a 4x4 antenna array at the front side, as you can see right here. Behind the active array, each element, we have a driver board and a final stage power amplifier. The final stage power amplifier is directly connected to the antenna element, and on that board we have an input coupler and the output coupler to observe the forward and forward wave at the input and output port to assist us to know what is the ARC and know the performance of the amplifier. And that design is actually also Aymeric using in his simulation, and this is a fabricated board. For both driver and the PA, that shares the exactly same design. Behind this PA boards at the back, we have the backplane, that's related to each cell. So for each chain, we have the input port and 2 port to observe the 2 couplers, and we also have the DC control to give the bias to the 2 PA board. Also, we have the DC control to the fan. And here another is a extra PC control to directly connect to the power supply. Before we assemble everything together, we have measurements for each component in the taskbar. This is the measurement for the 4x4 antenna array we have. Here for simplicity, we only show the highest coupling along E plane and H plane. So for E plane, we have a coupling level around -13.7, and that also gave us the highest coupling level. For the H plane, is lower, around -19, and reflection coefficient -14 dB. Here we also have the pattern measured and shown on the right. Here we picked 4 elements, and it's highlighted in this schematic. We have the corner, center, and 2 picked from the edge. So from the pattern, you can see it's kind of supports from -50 to 50 dB scanning. And then for the power amplifiers, we do injected the signal with 200 kilohertz OFDM signal, and bias we use 20 volts, and the current is around 100 milliampere as gain amplifier. We have tested all the boards separately, and you can see that's the gain curves shown here, and that's slight performance difference between each board, and we pick some typical performance of the driver boards on the left and final stage PA boards on the right. So gain is around 12 dB and P1 dB output around 24 dBm something. Right, and then we do the load pull test, not for the single driver or the PA, final stage PA board. We connect it together. For each chain, we do the load pull measurement, and we test it for all 16 chains. And here is also the contour. We picked the delivered power contour and the gain contour shown here. Plus that, to facilitate the ARC measurements in the future, we also calibrated the drivers. So here is a sketch of the active chain. We have the signal A injected, and you can see on the cell we have this SMA port for the input signal. For the input driver is to read in the forward wave input to the final state PA, and this we know the relationship between this B1 and B in, and this D in, and D in is measured from this port right here, so it's calibrated into the backplane. Also for the output wave, we have the B2. We have the coupling read as D out. Is the ports right over here. So noted here for the output coupler, we loaded with 50 ohm. It's possible to use that to read the reflected wave. However, if you enable the observation of both coupling ports at the output PA, the 2 signal coming in the coupling port, they won't mix together. So that's why we loaded one of them. And because we know the antenna S parameters, so here from this D out, we know what is B2. From B2 and S matrix, we'll be able to know what is the ARC seen by each power amplifier. As a summary right here, for our test bed at the RF port, at the RF site, we have the input control, which is the A wave you can see here. We have observation for D in and D out. And we also be able to measure the active reflection coefficient using the method just stated. For the DC parts, for driver and a final state PA, we have the DC control separately for the gain, drain, and also the bind sync. Especially here for the gate voltage, we added a variable resistor, so that enables with gate voltage tuning. Then with this test bed, we're moving to what tasks we can do using this test bed. Here is just a system block. You can see happening in the chamber will be only the active taskbar we have. And at the receiver side, we put the Hall antenna. So that can enable the OTA testing. For the taskbar, we'll be able to control all the TX chains with SDR platform we have in Heriot Watt. It can generate the signal to inject signal to the input port. It can capture the couplers waves, and that's enable the real-time monitoring. For the RX at the receiving side, if you want to match the pattern, get the E field, we can use spectrum analyzer or VNA connected to the Hall antenna. Or if you want to get the baseband, then we can use SDR to capture and read out the envelope. Also, we have the PC to control all the SDRs or the VNA spectrum analyzer, also the positioner that will help to match the pattern. It's not quite easy to match the pattern because our positioner cannot support very heavy loads. Then we have to design something extra to assist the pattern measurement. And here is the fixture designed by Samuel. You can see here that originally this is what we have as a positioner, and we're adding a base to taking the weight. Especially if you don't do that, then the small plate will take all the weight, and it's maximally can only take 2.5 kilogram. And then we add another rotation support. So then we reduce the torque, and equivalently, the weight applied to that small plate will be smaller than 2.5 kilogram. And that's for elevation rotation. And then all the weights go down to another plate, that's for azimuth rotation. That plate can take up to 79 kilogram. And here in this design, we have only 65 kilograms. So that's compatible with the positioner. And also another function of the structure is to shift on this dimension to align the antenna array center with the disc center at the bottom. Plus, we add some more flexibility to the structure, and it can not only support current 3.5 gigahertz structure. For future, we're expecting another 2.18 gigahertz taskbed, and that's also possible to use the structure for pattern measurement. Then go to what type of TX signal we can support to inject to all the TX chains. And on the right is the whole picture of all the SDR platform we have. Right now, for the TX, we can, 4 of them can go up to 75 max sample per second. So that 75 is 75 max I sample plus 75 Q sample, max sample. And that supports for 60 megahertz. For TX, we have 4 already realized, and we are targeting 20. For RX, we have 5 targeting 19. And it's possible to go even higher to 100 megahertz IQ sampling rates, and that support 80 megahertz bandwidth. Similar here, we have 4 enabled, 20 is working on that. And for RX, we have 3 enabled, and we're actually 16 of them should be available, and we're working on that. And for the waveform, if we want to do the CW with a single beam or multiple beam, we can already support 12 TX chains. And that requires a frequency synchronization, and you need to align the phase between all the TX channels. And for multi-tone signal, it's because sampling rate is like limited right here. But for like if the tone is spacing within 1 MHz, it's possible to do that. Still here we can support 12 chains, and we're targeting to enable 20 of them. Later, we're also working on to enable modulated signal that's definitely require higher sampling rates, like 100 Mach IQ sample. We have 4 realized and 20 is targeting. The problem we're facing here is to align the trigger between all the SDR, because otherwise the samples sent out will be messed up. Here just to say, because we need to do some phase calibration to make sure that all the TX, all the SDR TX, they are aligned with phase, and that's the method we use. Here we have just show how to calibrate fault chain. We use a 4-way power combiner, and each of the input is connected to one SDR TX chain, and at the RX we connected to the receiver of SDR. The method we use right here is we put the first channel as TX0 as a reference. Magnitude is 1 phase 0 degree, that's not changed because that's the reference. And then we turn on the TX1 as right here. We have the same magnitude with the reference channel, and we're sweeping the phase. For the other 2 channels, we give them 0 on the baseband, so we put the signal power to the minimum. And then by sweeping this phase on the channel, on the first channel, we can find a changing combined power at the RX. And if we read the minimum power, that gives us the 180 phase difference. And then we will be able to know what theta 1 gives us 180 degree out of phase point, and we will be able to know the phase difference between channel 1 and the reference channel 0. Then we repeat that for the second channel, and we turn off the first channel to get the phase difference between channel 2 and channel 1, and then we repeat for channel 3. So here, after that, we observe the waves on the oscilloscope. You can see that before we do the calibration, the phase is really random, and after that, we are able to align the phase. So that's why it supports us to do the multi-channel single beam or multiple beam forming. So go to a summary right here. Currently, our testbed can do a single or multiple beam with CW signal or with multi-tone signal within 1 MHz spacing. We can have 3 rows, that's 12 TX chains supported. Plus that, we can measure the active reflection coefficient as well. For multi-tone channel with higher sampling rate, like for example, like 100 MHz or FDM, we can only support 4 TX chain. And for that, we can do the OTA test to get the EVM as well. In the future, we're trying to align the trigger so that we'll be able to have more chains supported for the multi-tone signal, modulated multi-tone signal. And we're also trying to implement DPD on the SDR platform. Also, we're pushing to sign the pattern measurement feature for fabrication. And we are thinking of next active array version as well to add more flexibility to that. So in the future, we're thinking that each IF chain will be a modular, then we will have flexibility to form them into different topology. And that's all from my part. So I will forward this back to Aymeric for the task plan on this active array test bed.
Yeah, the point here is to briefly present to you some test campaign and some ideas we have to use the demonstrator Jiayu is developing right now, because we have like a lot of things and a lot of opportunities with this one. Of course, it would start with calibration. And so I won't go to fine details, but basically using mostly CW, we'll have to do measurement of radiation of active element pattern. We will do phase, so OTA phase calibration. We will also try to measure the received pattern to both compute the beam width measurement, but also to have the full performance of the system, both from the power amplifier point of view or at the EIRP point of view. So I won't go too far here. We have some details of the calibration that we'll do in the future. But I think what's really interesting is to go to the validation of multiple tones and of new radio or FDM signal. So right now, as Jiayu said, we should be able to work with 12 radiating elements at a time. And especially it's already possible for us to work in the average activation coefficient and the efficiency of the full system. So we can measure this from the signals from the couplets represented. And that's very interesting because that's the first approach to try to validate the different models we presented before. We can also work on the assessment of the power amplifier output spectral regrowth, again, with the measurement from the signal couplers. And eventually, when we'll have maybe the support for the mechanical rotations, we'll be able to work on the subcarriers EIRP patterns and the IMD EIRP patterns using a non-uniform space multiple tone signal. And well, all these measurements will be, of course, done changing the beamforming, changing the input spectrum, so with the tone spacing and the bandwidth, and changing the backoff at each iteration, trying to have like multiple data we can compare. And eventually, we'll try to do realistic OFDM approximation, so with multiple tones uniformly spaced, and then we'll be also able to compare all the results we obtain with the previous models with what we obtain with this demonstrator. The next task will be to work with modulated signals, so new radio or FDM signal, especially first to generate them and then to be able to use maybe until 9 elements at the beginning. And once we'll have this, we will again try to compute the average activation coefficient and the efficiency and to compare it with the model we have right now. We'll do the same for the output complex envelope, again from the couplers of the power amplifier. And eventually we'll be able to work on time varying EIRP and phase patterns compared with the models we have right now. Again, we'll try to do that for different beamforming, for different complex envelope. So changing the symbols, changing the modulation of our OFDM, and changing the backoff of the power amplifier. For this specific measurement, we'll have to take into consideration the measurement and the sample that must respect the sampling frequency of our OFDM signal. Again, we have more details about that, but it can be explained in the question and answer if you have some. But before that, I will let the lead to Weiguang.
We'll present our work on the power amplifier design for integrated multi-beam active antenna arrays. So as is introduced by Aymeric and Jiayu, our background is that we, in the large multi-beam active antenna arrays used in satellite communication systems, it's a trend to remove the isolators, which will cause the performance degradation of the power amplifiers. So our problem is how could we improve the PA performance degraded by the removal of the isolator when the PA is presented to the active reflection coefficients. So basically we have two tasks. The first task is we need to analyze the active reflection coefficients. We need to know what the distribution is like, and then based on the distribution, we could find a method to design our PA to get a better performance. Here is how we calculate the ARC of the active antenna array. So in the calculation, we take the PA nonlinearity into the consideration. Basically, we start from the incident signal and the lookup table of the PA load pool. Once we have the ARC and the input power, once we have the reflection coefficient and the input power from the incident signals, and we have the lookup table of the PA, we can search the complex gain of the PA to the signal, and we can, with the signal amplified by the amplifier, we could again calculate the ARC, and we can compare the ARC with the initial ARC. If there's a change, this means the ARC doesn't converge. We need to run the iteration again. And until finally we get the converged ARC, we use this ARC for our analysis. In our example, also for the 3.5 gigahertz testbed, now we have a 3.5 gigahertz 8x8 patch antenna array in the simulation, and we have the some S parameters for some adjacent elements here. For the signal generation, with this 8x8 patch array, we generate 8 beams and 60-degree maximum beam angle, and we use the standard LTE LTE standard to generate signals. Here we use 64-ohm OFDM, 12 subcarriers, 15 kilohertz subcarrier spacing, which is 0.18 megahertz bandwidth, and the sampling rate is 0.24 megahertz. We generate 100 multi-beam cases in total, and each multi-beam case is generated randomly, which means the beam direction and the signals are randomly generated. And for the PA, we have a 3.5 gigahertz total PA matched to 50 ohm, which is designed by Haijun in Heriot Watt University. And this is the layout of the DPA. And here are the performance counter measured as simulated at 25 dBm input power. And with the method we mentioned for the ARC calculation, we get some results for the ARC distribution based on the conditions before. Here we show the ARC distribution of 3 cases. From case A, all these 3 cases involve the nonlinearity of the PA, and the input power level is from 20 dBm to 30 dBm. The result is that we can see for different input power level, both the ARC, if we look from the ARC distribution, and if we look at the average value of the ARC and the variance of ARC, we can find that actually the ARC distribution is not affected by the input power level. And in our simulation, we also find actually the PA nonlinearity doesn't show much effect on the ARC distribution, which is maybe a potential way to simplify our analysis. And the ARC distribution is mainly determined by the range of the beam angle we defined here. So basically, if we have a large, for example, 80 or 90 maximum beam angle, the ARC tends to move closer to the center of the Smith charts. But if we have a smaller beam angle, like from 0 to around 40 or 45 degree, the ARC may shift away from the center of the Smith chart. Now we have the ARC distribution. We propose a method to design the power amplifier for this distribution. The idea is simple. We introduce an additional match network after the PA match to 50 ohm. And we have this ARC distribution. We know the average value of the ARC. We directly match the 50 ohm to the average ARC with a new match network between the PA and the antenna array. So here is the match network we use for the 50 ohm match DPA, and this is the average value of the ARC we get from the analysis. To verify our proposed method, we compare it with 2 other cases. The first case is we connect an isolator after the 50 ohm match the DPA, and then connect it to the ARC. And the second case is we remove the isolator after the DPA and connect the PA directly to the ARC. And the third case is our proposed method. There's a match network between the 50 ohm match the PA and the ARC. As the interface before the antenna array are different, so here we are not able to use the traditional performance for evaluation for PAs like PAE, gain, and delivered power. So here we use the effective ones. For example, for case 1, we evaluate the effective delivered power between the isolator and the active antenna array. For the second case, the effective delivered power actually is the power delivered by the PA, so they are equal. And for the second case, the effective power is the delivered power after the match network. And here we have different methods to calculate them. For the first case, the effective delivered power is the delivered power of the PA minus the insulation caused by the isolator and minus the reflect power caused by the mismatch between the isolator and the active antenna array. And for the second case, the delivered power, effective delivered power is the delivered power of PA. And the third case is similar to the case with isolator. We minus the insertion loss of the match network and the mismatch caused by the reflected power caused by the mismatch from the delivered power of the DPA. And we show the results in this figure. The effective delivered power, we can see that in all these three cases, the third case, which is proposed by us, always gets the maximum average delivered power than the other two cases. For case 1 and case 2, for each cases, we generate different input signals, so there will be a variance on their performance. But sometimes the case 1 gets a better result, sometimes the case 2 gets a better result, and this is within the accepted range because the outputs of the PA of these two cases are different, so it's not easy to say which case gives us a better performance. But if we compare these three cases, the case we proposed with a match network is the best one. This also works for the effective efficiency, so which is defined by the effective delivered power minus input power over the DC power. And in all these three cases, the case 3 gives us the best PAE, and this also stands for the gain performance. So with this comparison, we get two observations. The first one, to be more specifically, the average effective efficiency is improved by around 2.5% at 20 dBm in power and around 7.8% at 30 dBm average input power. And the average effective gain and delivered power are also improved by around 0.8 dB. Okay, so finally we come to our conclusion. The first one is from the ARC distribution analysis, we find that it's more determined by the antenna array itself, which is the S parameter matrix, and the beamforming strategy. So here, which means the maximum beam angle. And the second conclusion is that by matching the PA from the 50 ohm to the average ARC, we did get better performance than the 50 ohm matched PA case and the case with isolator. And for our ongoing work, now we evaluate all this at 3.5 GHz, and next we will shift the frequency to 2.18 GHz for the direct-to-cell cellular communication. And we'll also do some experimental verification using Doherty PA and the 4x4 pattern and array at 2.18 GHz. That's my work from.
Okay. So I will talk about the wideband K-band Doherty PA for satellite and 5G convergence. So I So this project, actually, I have this idea maybe 2 or 3 years ago, and this is funded by the Royal Society Research Grant. And the interesting thing is that 2 months ago, ESA released the same call, integrate the wideband PA for converged satellite and 5G communication in FR2. So it's very interesting to see ESA have this call. And I compare the requirement from my design with the ESA ITT, and we can see that the operating frequency, actually, because we have the same application, we targeted the same scenario. That's quite aligned quite well, right? And start from the 24 GHz to 31 GHz, and the output power, the ESA requires 30 dBm. We achieved the 34 dBm. It's good. And the power gain, and it requires 25 dB, but we have 10 dB, right? And because due to the chip size, so we use 2 stages to achieve this DPA. So if we would like to achieve the 25 dB, which means I think at least 4 stages needed for this PA. And the next one is power added efficiency.
Okay.
And we get the around 20%. Actually, they require 25. And because before they release this core, we don't have what's the target, but with some idea how to improve the efficiency. The last one is the power added efficiency, because they didn't give any specific requirement for the backoff. But I suppose for the 5G communication, especially we use the OFDM signal, so which means we need to have a high efficiency at the backoff, right? So this is we present this we give this the efficiency, right, at the backoff. And so then we can move to the details. So we have the 2 stages mimic power amplifier, and we use the 100 nano GaN on silicon technology. And so this is the chip. The chip I received 1 month ago, and so the picture I show here is taken in our lab. And the chip size is 3 mm by 2 mm, and the VDS is 12 watt. We because I received the chip 2 months ago, and the test is under preparation. So the specification I showed earlier is based on the simulation result, not the merit, right? I hope it will come out soon. Yeah. So for this wideband PA, so the bandwidth were around 20%, 25%. Right? And I also want to introduce some recent work. So because when we design the PA, for example, for this PA, for this chip, actually we have 30 variables inside. Actually, because it's a wideband operation, so we needed to take all the things at different frequency level, right? So we introduced the AI-driven PA design, which have published in the TMTT in February this year, and we introduced a circle model to model this EM simulation, because it will take a long time for the optimization for the things. So we introduced the circle model also combined with the AI algorithm to speed up the whole optimization process. And because the next one is because we talk about the 5G and satellite convergence, actually, so we also needed to combine filtering, and for example, also the filtering and the switch for the FEM actually is the front end module, right? So this is also the publication regarding the wideband filtering switch design published last year on transaction MTT. And yeah, because I designed the wideband Doherty PA also designed the wideband filter. Actually, I think they share the common space. So actually, they have the knowledge can be transferred both for PA design, also for the filter design. And but what depends, because they have different requirement or different specifications. Actually, it can be used for maybe the boundary between the filter and the PA or other things will become blurred because they can share some common structures. Yeah.